Hi guys, welcome. In this video, I'm gonna teach you about the equivalence of second order dynamics of RLC circuits and mass spring damper mechanical systems. So what is this all about? Let's say you have a mechanical system and an electrical system, and in some way, shape, or form, this system will behave the same. What do I mean by this? That when you solve this system and you have and you get the transfer function for it, you will see that these two different transfer functions will have the same behavior, right? They will have the same form. Now, to understand this better, instead of starting with the RLC circuit, I think it's better if we start with an RC system and then so we can see what exactly makes them equivalent, and then we can check out the RLC system. So let's say now we have this mechanical system here. This can represent any form of system, really. Nothing physical right now, but you can also do this for like dampener transmission system in the car. So when we solve for these for this system, our transfer function is gonna look something like this. So we can clearly see here, this is a second order system, and we have the same thing for our electrical system. So let's take a closer look at this system here. So they clearly share the same format. So here you have a constant +1, and then here you have a constant +1, and it's the same here, and it's the same here. And here you have a constant 2 multiplying s, right? So these are basically, they have the same format. So what can we imply here? Just by looking at the equations, I can see basically that we can do make these two terms equal, right? So if we were a v1s over k1 plus 1, we can make it equal to r1c1 s plus 1. So right off the bat, I can see here that our b1 is equal to our r1. So this makes sense, right? Our dampener, which is the b1 here, has a similar effect on the system as a resistance. So this slows the movement of the system, and this creates resistance for the current, right? So this makes sense. For the K1 here, we have a different thing. So 1 over K is equal to our capacitance. So this is known as the inverse spring constant. So what this is basically saying is that a capacitor is like an inverted spring. And we can make some more comparisons. So if we have the resistance, and then we have the 1 over c, or 1 over k for c, the velocity of our system can be compared to the current of our system, right? So how many electrons are moving to this through this circuit is comparable to the velocity of our mechanical system. And for example, the position of this mechanical system, something to compare it to is when you analyze an electrical circuit on time, the capacitor charges and then discharges. So the capacitor can be used to measure time, or in this case, position, right? So voltage as capacitor is the same as position. And force, let's think more about the potential force of the system. So if we had an input force here, this would be the same as the voltage of our system. So now going to an RCL or LRC system, if we have a second order system, one thing that was missing on the other system was the mass. So we know that any second order system following Newton's second law can be defined by this second order equation, which turns out to be this transfer function right here, right, for an input u. And same goes for RCL circuits. We can also define any series RCL circuits with this transfer function. So here it's even easier to see what we had missing, right? If we look at a template of a second order degree transfer function, we know that they all follow this rule. So we have the same thing as before, where we can equal our two equations, and then we can draw a conclusion for here. So the inductance of an electrical system is the same, or has the same effect on the system as a mass. And again, dampening is the same as the resistance, and K is the inverted capacitance, right? So if we have quick example here, here's our completed table. We're missing here force, which is the voltage. And then, but let's say you have this RLC system, you can directly convert it to an analogous mechanical system. So how would you do this? So first we have input current, and this would become an input velocity in this case. And then we have a resistance, and this could directly be a dampener. And then we have an inductance, and this just becomes a mass. And here we have another dampener. And here we have a capacitance, and this becomes a K, a spring. So you can get this equivalent mechanical system, which we will have the same response overall of the system. Thank you. I hope this helped you to understand how one system can be equivalent to another, and that's it.